the next speaker is Mejdi Azaiez from the University of Bordeaux, who's going to be talking about certified ROM for parametrized AC equation. Thank you, Mejdi. Take it away.
Merci. Okay, AC is Allen-Cahn. Okay, and let me first introduce what is this equation. And this is the contents, but let me start with the first one, gradient flow model. Okay, let's say that we, with the collaboration with Thomas and some of Chinese colleagues, especially who is a PhD student, we are working on the possibility to reduce and to write reduced basis to solve the problem described by the equation that we call gradient flow, in the sense that we have a time evolution problem, but on the right-hand side, we have the gradient of scalar function, and the scalar function from the physical point of view is called free energy function. And usually it is associated with some physical problem, and I will show you one specific energy function that we are interested in, and it covers the application. Okay, this is 1.2. It's a very, very interesting relation in the sense that we have to respect the following energy dissipation. And this has to be verified by any scheme and also by any reduced basis. So let's say that from the mathematical point of view, we are trying to investigate a family of reduced bases that answer to this kind of problem. And you know that we have two possibilities to consider the gradient. One, it is to use the L2 scalar product, and in this case, you are going to make some computation, mathematical computation. So you can, with the L2 scalar product, we can prove that very easily prove that in this case, the gradient of the energy is given by 1.5, and this corresponds to what we call Allen-Cahn problem. In Allen-Cahn problem, we have the time derivative, and you have the Laplacian with epsilon, and you have the derivative of this function that contain the, let's say, the derivative of the energy that we are considering for the system. In our case, once again, we limited ourselves to this model of energy, what we call the Lucensburg-Landau energy. And when capital F is equal to 0, it corresponds to Helmholtz energy. And in our case, we keep, of course, the nonlinear term given by capital F. You fix that in Allen-Cahn, so we consider this nonlinearity that we derive, and we keep it for the Allen-Cahn problem. If you consider the same question by not with using L2 scalar product, but using the definition of H minus 1 scalar product, you can immediately prove that we will derive what we call the Cahn-Hillary model. So by conclusion, Allen-Cahn is the L2 derivative and the gradient, and Cahn-Hillary is the H minus 1, and both of them, they are here to derive the same energy function that I presented before. In our case, we will limit our presentation to the Allen-Cahn. Nevertheless, I think going with Cahn-Hillary is a very interesting problem, and I know that it represents more complexity, especially for the way to produce snapshots and to produce the right scalar product to correlate. Okay, why we are working on this question? Because we have some link with the question of energy. And in our case, the function phi, that is the solution of the gradient flow, is what we call the phase field. It will be equal to 0 or to -1 in one region and the 1 in the other one, and in between, we have the connection between the two. And we are coupling this phase field to, for example, here, to energy equation, and namely for our case, it will be the pure conductive problem. That's why we have no velocity, no pressure. For the moment, we have just conduction, and we will heat by conduction, and we will couple the phase change phenomena will be taken into account thanks to this model, which is the phase field. You see that we have on one hand, nonlinearity. We have coupling the temperature to the equation of temperature, and in the other side, when you solve the energy equation, you have to adapt the conductivity, we have to adapt Cp and the other with respect to the value of phi. This is, once you couple the two equations, you are able to simulate how you can change the material from solid to liquid or liquid to solid. And you can even consider more complex situations. Let me give you a very, very simple case. In this case, we have the box and we heat everywhere the boundary. And you put temperature, for instance, here about 600 degrees. And we can see that blue is liquid and red is solid. And we can go to, let's say, make the fusion of all the box. At the same time, we present how the temperature is evaluating. So this is one of the applications we are working in. And this is a very, very easy case that I share with you. It can be more complex in the sense that we can also consider such kind of interface. And we can also see that for this case, the method works quite good. In any case, it's very CPU time consuming. I mean, some kind of cases that maybe can take hours and days of, especially for 3D, time to produce the result. That's why we are considered that it is more than urgent in parallel to produce this full order model and simulator. We think about reducing one. Okay, so let's focus on Allen-Cahn, and the first one, 3.1, it is for a given parameter. You start by the parameter, and in our case, the beta will be our parameter. But in this version, we have one parameter, and we look for the solution U. This is the phase field, that it is verifying this equation. And beta, it is the ratio between gamma and epsilon. And keep in mind that epsilon represents thickness. And usually thickness is about 10 to minus 4, 10 to minus 3, and this can be very small. So it means that the presence of the nonlinear term is quite important on the model. So for a given beta, we want to solve this. And on the other hand, we consider that if we are able to reduce for one beta, we should think about what's happened if you keep time fixed, keep space fixed, and we try to solve for the family of beta. That's why the second part here is to present the version of the parameterized one. So now we are adding some kind of variable, which is beta, and which will be between beta minimum and maximum, and it will evaluate in this interval. And we want to solve a family of Allen-Cahn problem. And we want to, by the way, to solve this problem for almost everywhere beta in this set. Okay, we have some hypothesis that is has to be verified for mathematical reason, but it is absolutely the case, at least for the energy we are considering for the capital. Mathematical is not constrained for our physical problem. Okay, so let's go with the variation formulation. If you are one beta, the natural variation formulation is given here. Okay, this is very classic. And of course, if you look for the problem with different value of beta, one way is to increase the dimension of your problem. So the problem, as you can see, the solution is not U, but U bar, and it is in L2 gamma. It means that your solution depends on beta and time and space. And you can see that the variation formulation that add the presence of the parameter. So you have to have some kind of scalar product for time, space, and even for beta. And 3.5 can be, for example, solved with the technique like adapt PGD maybe, or something like this. But it means that we can solve in the hypercube this problem. Okay, so let's start with the first point. Let's fix beta, and let's say a few words about our strategy. We make time integration. We have finite element for space. This is very classic. And to fix our way to produce snapshot, we considered this solution, this strategy, but one can use any other method, and you can apply your favorite method to approximate this nonlinear problem. For our case, we considered what we call the stabilized first order semi-implicit scheme. This is because it's very, very rapid to implement. I mean, if you put this 0, this is implicit for diffusion and explicit for the nonlinear, but you know that it is not unconditionally stable. But if you add this number, you make it unconditionally stable, and you make it verifying the fundamental decrease of energy, and so becomes something very, 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 very let's say, is good to produce snapshots. This is our finite element, and this is the approximation. I mean, that's the problem we solve with finite element. And even for the finite element and time approximation, we can show that we have a good approximation in the sense that the distance between the solution, time and space approximated, verify first order and the order of the finite element, and we have exact information about the constant. Okay, now let's go with snapshot. The snapshot in this case are given by the classic one. Okay, I mean, you take the snapshot for each time step, and we add a variation in time. So we add the derivative in time. Some of you know very well this kind of snapshots, and I will show you what is the interesting, what is the added value of using this kind of strategy in our case. So once you do this, you continue like any POD technique, in the sense that you ask to minimize the distance between the projection and the solution snapshot itself. It takes you to the road of the matrix, eigenvalue, eigenfunction, and you have the classic problem even for this way to produce snapshots. Okay, so you can also prove with this technique, I mean, with adding the derivative in time, that the approximation between the finite element and its projection on the reduced basis is controlled by the residue of the eigenvalue. So we recover the classic solution. This is not new, but it is new in the framework of Allen-Cahn problem. So we have this interesting relation. And this is 3.21 is something that 3.20 is very important. It means that even the reduced problem verifies the energy dissipation, and it is a welcome property. And we also verify that the distance is controlled by the residue. The constant exponential beta is very classic in this case. And this is what we have to verify. I mean, once you produce your finite element solution, once you have the exact solution, you can control the distance between the two, and the distance first order in time, it is HM if you have M finite element and the residue. Okay, and from the numerical point of view, we succeed to verify all this for a given beta, please, for a given beta. And let me tell you why we were interested by adding the snapshot which contains the derivative in time. Because when we start with the classic snapshot, they have here contain delta t in the denominator. We used to have this constant divided by delta t, which is not quite interesting in the sense that when delta t is small, this error becomes not very, very well controlled. So when we try to ameliorate the mathematical proof, we can clearly see that it is better from the mathematical point of view to not consider the classic POD snapshot, but to add the time differentiation. And by the way, once we do this, we have this inequality and no more denominator with delta t. So we ameliorate, we put it even optimal approximation for L2 and even more than L2. Okay, so we were happy because we make it better than the work given reference 1. It was published in 2021. And now we can, once we are confident with one beta, let's go with different beta. I mean, let's go to the parametrized problem. And we consider the same problem, but we vary beta between beta mean and beta max. And now we imagine that we consider the snapshot in time, derivative in time, and snapshot in parameter. And we put all this, what we call U union, okay, that contains something very in time, something very in beta, and you classify this correctly, and you apply your strategy to produce POD and eigenvalue, and the roadmap is the same. And you have here the same theorem. You can prove easily this kind of residue. And you write also the discrete problem for the reduced model. We are projecting an XR, which is spanned by the basis reduced before. And you work a little bit hard, but little bit, and you can prove the following result. I mean, you can see here that we can control the distance between the expected solution and the reduced one, which is given by this constant. And we have, since we are using first order time to approximate the time, that's why we have delta t. We have the classic error and finite element, and we have delta beta. Delta beta, it is the parameter step that we consider to approximate the sample in beta. And we have this constant that is applied to the residue of eigenvalue, and this comes from the fact that we are multiplying the problem on beta. So we have it for L2 error, and we have it for H1 error. And now we have to go with numerical verification to prove that the theory is, not say correct because we proved the theorem, but it is verified, and it fits with the numerical experiments. Okay, let's go to numerical results. The first one we'll consider for given beta. I consider this initial guess, and to be more comfortable with our simulation, we need to add the right-hand side. Otherwise, it's not easy to. We can produce some solution, but not very rich to represent some nonlinearity, some complexity. So if I fix one beta, I would like to prove this, and it is given here. You can see one comparison. You can see that with blue we have the classic snapshot, okay, and with the other one we have adding the time derivative. We have differentiation, and we can see for both cases we are able to solve. We propose the reduced basis, and we can see that the error is going exponentially to 0, and we have also some kind of gain to use the derivative in time in our snapshot. Okay, let's go now with the other question is to consider different, we start with many beta, and the beta parameter going from evaluate between 0 and 100, and you fix one beta which is not in the sample. Okay, this is the target, this is new beta, and we solved the problem for different other beta. And we are expecting this kind of approximation. So it means that I have to control that everything runs well, delta t, hm. Since I am first order and finite element, which would be H2, because the space step is constant. So we gain one order for finite element. Okay, we can see that for a fixed delta beta equal 10, for a finite element equal 100, 1 over 160, and the residual is enough small. So everything is enough small in the previous inequality, such a way we can see the effect of delta t. This is what we used to do when we have many parameters in the inequality. Okay, we can see that I am decreasing, and I am also first order time. Okay, if you divide by 2, I almost divide by 2, by 2, by 2. So, mean that the reduced model with the reduced basis for the parameterized problem using the strategy follows the first order in time. Now let's go with the delta t. Let's suppose it it's supposed to be enough small. Delta beta is also equal 10, and so we can see the effect of the finite element. And that's why we have this, and we can see that the local error for this case is about 2. And now we try to to see the effect of delta beta. Delta beta is, remember that I have my parameter set, and I choose delta beta to define the number of snapshot and beta that I have to consider for my to build my reduced basis. And we go with this, and we have more than first order. We have something of 3 or 4 order, which means that we have better convergence. This is something that we do not yet understand. from the mathematical point of view. Nevertheless, our theorem is not, it is sufficient. I mean, we are not proving that our inequality is optimal. We prove that it is on delta beta. We do not prove that we cannot do better. From the numerical point of view, it seems that we have superconvergence in delta beta. Here also we have some comparison between Rome and the exact solution, between firm and the exact solution, and we see that we have decreasing. This is the computing with delta t equal 10 to minus 2. And the right-hand side, we have the order of reduced basis, and we have L2 error between Rome and foam, and the residual. We can recover the theorem that we did before, and the condition of given by the parameter here. And in this case, what we are doing, we are fixing all the parameters, and we try to see the error for different beta. Okay, and we see that we have this kind of error. I mean, in the limit, left and right, we have decreasing. We have an optimal value in between, but it remains between, let's say, 10 or 6 to 10 minus 4, so it remains in the good resolution. This is the value of beta and the L2 error between Rome and foam, and we recover this, the classic behavior between when we vary beta from the lower bound to the upper bound. So, by the way, we did some numerical result to be sure that all the what we found in the theorem, I mean, the approximation in time and space and parameter are fulfilled with the code, and now we are confident in the sense that the reduced model that we are proposing is certified, and now in the same time we continue. We did a second part of this job, which consists in proposing an a posteriori error, and we succeeded to have one and to prove it. And this is the second part. Maybe I will present it for next talk. And now we are coupling also this model by energy equation, so to be sure that we are able to simulate and to produce phase change phenomena to storage energy in 2D and 3D, and even in the geometry that was presented by Juan, and to contribute to the objective of parabolic storage energy. So all this is done in collaboration, as I said before, with Thomas' team and Juan Valverde. We are results, so it looks positive in the sense that we from 8 we go to 1, and this looks positive, but we are expecting better and more interesting result with the 3D case. For the moment, we have only 2D results. Okay, we reached the end. Thank you for your attention. I'll be happy to answer to your question.
Very nice. Thank you, Mehdi. Very nice talk. Any questions from the audience?
Yes, I have a question. Do you hear me?
Yes, sir.
Sure.
Yes.
So, hi, Mehdi. Very nice talk.
Hi, Angela. Merci.
Can you give us a hint in understanding why the fact of adding the derivative in time of the solution is so good? And I tell you why it's something which I am asking myself. It's because if you add the solution in time, is as if you are adding two close by solutions, right?
Yeah.
So is it because you are putting in the database solutions that are far apart in time, such that when you put the time derivative, you are putting close solutions that are close in time, in a sense? Is it so? In other words, let me formulate the question another way. If you put many snapshots in time, okay, let's say, one snapshot for each. Also, suppose you have an explicit code, right? And you put one snapshot for each instance, for each time step. Would it be still so good to add the time derivative? I don't know if I was clear.
Yeah. I think I understand your question.
What is your?
The best way is to conduct the numerical experiments, because we have the possibility to conduct it. Okay. On the other side, you are telling what's happened if I make the delta t very small.
Yes, and I make the delta t very small, and so I add many time snapshots in a sense, right? So what one would guess that if you do that, then the influence of the snapshots of the time derivative is less. Okay. But I don't know if it's a good guess.
Yeah. I think first we can try this, and I think you are right. But let me tell you once again why we were conducted to consider this question, because in the reference that I'm presenting here, I don't know if you still still have the presentation. Sure. The paper they produce it for one beta, for one given beta, one parameter. They are proposing an error. And in their proof, they have the constant divided by delta t. Okay. Oh, I see. And when the student who was considering their proof, he reproduced the proof published in the paper. And when you have delta t in the denominator, your first action is to say, maybe we can do better. We can take it out. Okay. Yes. And he was following the proof, and he said, okay, if now I change the scalar product of the snapshot and I put the variation, I reproduce the proof, and this 1 over delta t will disappear. Okay, so it was really from the mathematical point of view, to improve one inequality, which is very amazing. Okay, in the same times, at least for the range of delta t that we considered in our numerical experiments, we have some gain, but I'm not sure. I'm really not sure that when delta t is going to 0, we will have better information, or we can get better. I'm not sure. I know that I had this question before when I was with Sevilla, or I think it was during the Congress in Spain last summer. Okay. I think to make the numerical experiments, but I'm not sure that l'affirmation universelle.
I see. Thanks a lot, Mejdi.
Very nice. Any other questions for Mejdi?
May I ask one?
Absolutely, Francesco.
So it's still again on these couple of slides. Is the factor 1 over delta t tied in any way to the choice of the time stepping scheme?
Sorry, I'm sorry. I didn't understand. Say it again.
Does that depend on the choice of the time stepping scheme? Like if you change the time integration, would maybe the power of delta t change?
You mean the approximation between this the finite element solution and the reduced one?
Yeah, there, or even in their original proof in number 1.
in this work, from the mathematical point of view and from the numerical point of view, we have this. I don't know if you see 3.22. We have delta t. We have this. Okay. And the question is, yes, we don't have better, we don't have worse, and let's say that the question that was asking before is the affirmation that I'm giving here. You see, to present that one is better of the other. Is it universal? Is it for every time step we have this quality? or maybe we can have the same curves. The blue will be on the red one.
Okay, thank you.
I mean, the error is controlled by delta t. The error is controlled by delta t when you use first order time scheme. This is what we proved, and this is what we verified, at least for some numerical experiments.
Yeah, I think Mejdi, I think that what Francesco is asking is okay, but this in reference one.
Yes.
He's saying, Francesco is saying, oh, okay, so in their proof they got 1 over delta t. Yeah. But maybe if they chose like a different time discretization, maybe, you know, the 1 over delta t.
Sorry. Yeah, thanks for. Okay, I'm sorry. I don't know.
I don't think
what is sure that if you go with this scheme and we consider what we did, we let's say we make it better. Okay, we make it better. I don't know. We didn't try. I don't know. I think now we have to consider this question. Yeah, it's true.
So. Can I add a quick comment? So I really like the questions by Angelo and by Francesco, and I think that there is quite a few papers on this. I think the general feeling is that in general, so it does not depend. Yes. It's not about it's not about this particular application to Allen-Cahn, but in general, I think that you still get 1 over delta t terms. I don't think that it matters the type of discretization. So we've seen this for a bunch of discretizations. And I think it's not about the discretization, but it's about the fact that if you don't take approximations of the time derivative, when you do prove the error, you do get a 1 over delta t term. So it's the suboptimality of the
and when you add the time the differentiation, we take it out. Okay.
Correct. Right. And I just want to say one more thing. So this was first proposed without optimality by Kunisch and Folkfein, so 20 years ago. So they did use in their paper these difference quotients, and then Sorensen in 2010, when he proposed the discrete empirical interpolation, he made the following observation. He said, if you approximate the time derivative, is the same thing as approximating the right-hand side that includes the nonlinearity. So in a sense, including snapshots of the time derivative is similar to including snapshots of the nonlinearity, as people do for time and dime. And I think it's a very interesting remark, right? So you add information without paying any price. You don't compute anything new, but then you add information, you reorder the eigenvalues with respect to this maybe nonlinearity. So this is maybe related to the question that Angela asked, and I think it's still open. So yeah, I mean, it's an interesting question, and kudos to Mejdi for very nice Allen-Cahn type of numerical analysis.
Okay, thank you.
Thank you all. Thank you, Mejdi, for this very nice talk. And I will let Angelo maybe say a few words to close the very nice seminar.
Thanks a lot. Thanks to the speakers. Thanks, Traian, for chairing this session with great authority. And so probably there will be a new seminar in January 2023, and it will be around the test cases that Tommaso Taddei was with the other colleagues are preparing. So stay tuned, and stay tuned also for the next ARIA conference. So thanks again, and take care.